come from a very diverse background, so it will be mostly about some basic concepts. And I've written a note about this, and I will send it to the organizers, so it will be posted online. So the plan is to go through some of the basic concepts behind en route effect, mostly. I will discuss several different perspectives of understanding the en route effect. First, I will discuss the Euclidean perspective, which I think Professor Hartmann already talked a little bit about in his talk. And then I will discuss a Lorentzian perspective. And then I'll discuss how to compute the stress tensor, for example, for a render observer. And then I'll talk a little bit about some more physical setups involving the so-called en route detector. And then I'll generalize the idea of the en route effect in flat space to the black hole background. I will be a little bit brief about that. I will talk about the near horizon geometry of the black hole and argue why you can apply the flat space discussion to the black hole. And then I'll use the analogy to flat space to discuss different vacua of the black hole. Okay, so let me start with the first discussion of the en route effect and about the Euclidean perspective. So I know that the Professor Hartmann already talked a little bit about this, but let me just repeat some of the things that he already said. Let's begin with the metric of a Minkowski space in D dimension. So as we all know, let me first draw a diagram with the time direction and the space direction. As we all know, if we want to prepare the vacuum state at, let's say, t equals to 0, we can first do a weak rotation to Euclidean space. So let me replace t by tau. Well, tau is equal to IT. Now we can prepare the vacuum state by doing now a Euclidean path integral from tau equals to minus infinity up to tau equals to 0. Okay, so that's how we prepare the Minkowski vacuum. And if we want to compute some correlator in the vacuum state, it's very simple. We can insert some operators in the path integral and simply do a path integral from tau equals to minus infinity to tau equals to plus infinity. So this is the standard weak rotation of the usual path integral. The reason we want to talk about the Euclidean path integral is because there is an equivalent perspective to look at this path integral. Rather than looking at this path integral from minus infinity, tau equals to minus infinity to plus infinity, we can choose a polar coordinate where tau is equal to r cosine theta. And let's choose one of the spatial coordinate x1 equal to r sine theta. So this is just the standard polar coordinate, where r is the radial direction, while theta is the angle direction. And we slice the space-time according to the constant theta slices, which means that we slice the space-time like this. Okay, so each of these slices, they correspond to a fixed value of theta. And we view the path integral as going in the circle direction as generated by the translation in the theta coordinate. In this, in the r and theta coordinates, the metric becomes ds squared equals to r squared d theta squared plus the r squared plus some transverse space, which now is little d minus 1 dimension. And theta ranges from 0 to 2 pi. So the idea is that we view the path integral as going in the theta direction, and it has periodicity 2 pi. So the new perspective is to think of this theta as the new Euclidean time, which is now defined not from minus infinity to plus infinity, but it's on a circle. That's why we can think of this path integral as computing a thermal trace, namely trace e to the minus 2 pi, which is the period of the theta coordinate, times the Hamiltonian that generates the theta translation. Okay, so this is just the equivalent way of thinking of the path integral, computing the partition function of this space. So here, let me mention just a few subtleties. Strictly speaking, since the circle direction, since the circle here, it shrinks to a point at the origin, this computation does not obviously have a trace interpretation. So this is related to the fact that Professor Hartmann mentioned in the talk that there is some issue about the UV divergence near the origin. So in this talk, I will not be dealing with that. What we can imagine is that we either put the system on a lattice or we cut out a small tube around r equals to 0 with radius epsilon and taking epsilon to be very small so that the circle does not shrink to a point and the calculation indeed has the interpretation of the trace, okay? And in my note, I have a reference which will direct you to a more rigorous treatment about the UV issue in the quantum field theory. The second subtlety I want to mention is that, so if you look at this expression, it's very tempting to interpret beta as the inverse temperature. But let me remind you that the temperature should have the dimension that is 1 over length. Or in other words, the inverse temperature should have the dimension that is length. So it cannot just be a number which is 2 pi. So the reason is that the more proper thing to say is, the more proper quantity to look at is not really this 2 pi, but rather the proper temperature at some radius r. Okay, so how do we look at the proper temperature? To look at the proper temperature, we should look at the proper length of the circle at radius r, which is simply 2 pi r. So beta at location r should be 2 pi r, which tells us that the local temperature should be not really 1 over 2 pi, but really, rather being 1 over 2 pi times r. Okay. Of course, here I'm just talking about a Euclidean calculation, and the notion of the temperature is not very clear. To really talk about the meaning of the temperature and to draw a connection with a constant accelerating observer, we need to go to the Lorentzian signature. So to go to the Lorentzian signature and draw a connection with the so-called Rindler space is very easy. What we do is just to take this metric and analytic continue the theta coordinate to be theta equals to I eta. And that will give us a metric that looks like ds squared equals to minus r squared, the eta squared plus the r squared plus transverse space. So if we look at our Minkowski diagram in the Lorentzian signature, this metric covers only part of the space-time. It only covers part of the space-time that is the right, so-called right Rindler wedge. That is, if r is greater than 0 and eta is between minus infinity to plus infinity, it covers this part of the space-time. Of course, we can also take r to be a negative number, and that will cover the left Rindler wedge. Okay, so this is the so-called Rindler coordinate. Now, we can ask, yes.
Yiming, can you again give the argument of this beta equals to 2 pi r? So you drew a circle and then you circumference is 2 pi r. So how does it relate to temperature?
Yes, I will mention it in a moment. So to really discuss the temperature, we need to go to the Lorentzian signature and ask what temperature really means. So now let me come to this question. We need to answer the question, what is an observer that stays at constant r, okay? So that's why it is related to a constant accelerating observer, Because if we draw the wall line of observer that stays at constant R, we see that it goes on a curve like this. So this observer first comes closer to the origin, and then it travels to infinity again. And the trajectory of this observer is given by, let's say that it crosses the horizontal axis at R naught. Then the trajectory is given by t equals to R naught sin eta, and x1 is equal to R naught cos eta, okay? And you can easily check that this wall line corresponds to an observer that has constant proper acceleration that is given by 1 over R naught. This is intuitive because if R naught is greater, then the acceleration of this observer is slower, as you can directly see from the picture. Now, when we talk about temperature, temperature is always measured by measuring energy. And when we talk about energy, we are talking about the energy as measured by this observer. And how does an observer measure the energy? He measures energy with respect to his proper time. So the way that an observer defines energy is always defined with respect to his proper time. So what is the proper time of this accelerating observer? Let's see. So we can compute proper time by just computing d tau square. By definition, is equal to dt square minus ds square of this observer. And we can plug this into the formula and immediately see that the d tau square is given by R naught square d eta square, okay? So we see there is a proportion, tau is not exactly the eta coordinate that we mentioned, but tau is given by R naught times eta. So as I will later argue more carefully, the temperature that we computed here, this beta is the temperature, the so-called temperature with respect to this eta coordinate, because it's this eta coordinate that that is the analytic continuation of the theta coordinate. That is a circle with length 2 pi. But if the observer is accelerating with acceleration 1 over r, his or her proper time is not exactly eta, but up to a constant r naught. So the temperature, as measured by this accelerating observer, should be 1 over 2 pi r naught, because it should be measured with respect to his proper time. Okay, but I haven't really told you how this observer really measures energy or measures the temperature. I will talk more about that in the en route detector part, but here let me just give you a simple example. Let's say that we have a scalar field, a massless scalar field propagating on the space-time, and let's say that this observer is measuring some 2-point function of this scalar field. So let's say the observer travels along this line, and this observer measures the 2-point function of scalar field phi at this point and the scalar field phi at that point, okay? What I will argue is that this 2-point function takes a form that looks like a 2-point function in a thermal state. And the way that this 2-point function decays matches this temperature. So let me tell you how to show that. So of course, since the state is just a Minkowski vacuum, it is very easy to, yes.
Yeah. Mm-hmm. So I mean, the temperature should be, in a sense, proportional to 1 over mod R naught, right? Because we can take R naught to be some negative values as
yes,
as
exactly.
Well, right?
Yes.
Okay, fine, yeah, good.
So here I will be mostly just assuming that we are thinking about the right Ringler wedge, so I don't need to do that. But that's right. So let me backtrack a little bit. So what I actually just did is that I argued that a constant accelerating observer lives on this line that is at fixed R0, and it travels along the Keating vector that is the generator of the eta translation. So eta runs from -infinity to infinity. And one physical way of thinking about the temperature as measured by this observer is to think of what for example, the 2-point function of the scalar field that is that this observer measures. So we can now compute this 2-point function. And the 2-point function, it's just in Minkowski vacuum, so it's super easy to compute the 2-point function. And let me first compute it in, let me just first write down the answer in Euclidean space. So in Euclidean space, the 2-point function of a massless scalar in 4 dimensions is just given by up to some proportional constant is just given by tau1 minus tau2 square plus the distance, the distance square. Okay, and we can just do a simple change of coordinate and put it into the r and theta coordinate, and then continue to Lorentz signature. And that will be, this way will be particularly easy to compute the 2-point function of the scalar field along such a trajectory. So in terms of the r and theta coordinate, the 2-point function is given by r1, let's say the first scalar field is at r1 theta 1, and the second is at r2 theta 2. And let's say they are for the rest of the dimensions. So this only cover t and x1, and we also have x2, x3. Let's say they sit at the same location at x2 and x3. So if you just do the same change of coordinate, you see that it is given by r1 minus r2 square plus r1 r2 times sine square theta 1 minus theta 2 divided by 2. Okay, so this is just I just did a change of coordinate, but the reason I want to work in the r and theta coordinate is because the analytic continuation just in theta simply gives me will be particular. The analytic continuation will just suits the Rindler coordinate in the right wedge. So let me continue theta to I eta or minus I eta. I will just get phi of r1 eta 1, phi of r2 eta 2. That will be given by, so r1 minus r2 part will not be changed, minus r1 r2 sinh eta 1 minus eta 2 square divided by 2. Okay, and let's say that the two, let's consider the case that we are looking at a constant accelerating observer. So it sits at a constant radius. So R1 and R2 are both equal to R0. And then we can simplify this expression to -1 R square R0 square sinh of the delta eta divided by 2. Okay, so we see that a long time separation, let's say delta eta is very large, goes to infinity, the 2-point function decays as exponential of minus delta eta. Okay, but again, as I emphasized, as this constant accelerating observer, this observer measures the 2-point function with respect to the proper time rather than the coordinate eta. So we should better convert this into the proper time. That is easy. It will just be e to the minus, let's see, tau is equal to R0 times eta. So it will be delta tau divided by R0. Let me remind you that in a thermal state.
Yiming?
Yes.
So this R1 and R2, so you set them equal to R0.
Yes.
R0 is the distance I mean, the way you drew it in the diagram, does
Yes,
that work out?
R0 is this one.
Yes.
It's the
So,
distance from the origin. Yeah.
but the places where you put your 5 fields, are they also at R0?
Yes, I'm imagining that an observer is traveling along this line. So for example, he excites a quanta at this point, and then he absorbs a quanta at that point, and he measures the 2-point function of the 5 field. So both of the operators are inserted along this line.
This is a constant acceleration line. So, but in these coordinates, can you say that it's also separated from the, so it always has a constant distance. So R in your original thing in the UK.
Yeah, I understand the question now. Okay, so that's my bad. So in the regular coordinate, in this coordinate, the constant R slice is simply this curve that travels like this. And I guess what you are asking is that, let's say the distance of this point, whether the distance from this point to the origin, whether that is R0 or not, is that the question?
Yes.
Okay, let's see. That should be easy to figure out. Yes, I think that's also R0. The reason is that this line is generated by a boost, which is an isometry of the Minkowski space, and the distance between these 2 points is invariant under that.
Okay.
So the proper distance from this point to that is also R0.
All right.
So the notation is good. Yeah.
Okay.
Okay. So now I've argued that the 2-point function decays with the difference of the proper time like this, and the reason that this expression is illuminating is because if we consider a thermal state, in a thermal state, the 2-point function in general, if we consider one at time t and the other at time 0, it decays as exponential to minus 2 pi t over beta. So this is a generic behavior that you will find either in all kinds of quantum field theories. And we can just compare these two equations, and that will tell you, so this beta is inverse temperature. That will tell you 2 pi over beta is equal to 1 over R0, and that tells you that the temperature as measured by an observer at radius R is given by 1 over 2 pi R0. Okay, and R0 is equal to that. So this is just a quick way to see that this temperature is really the temperature measured by the constant accelerating observer. Later, I will talk a little bit more about the so-called en route detector. That is what a detector that this observer brings will actually detect. That is a more physical way to think about it. So before I end this part of the Euclidean discussion, let me pass by emphasizing that this kind of construction is very general. It's general in maybe 2 ways. So it's very general. The first way is that it does not really rely on that the quantum field is a free field or is like scalar field. It will apply to interacting theory as well, because here all I used is some path integral argument, and that is pretty much very general. And the second reason that it is very general is that it applies in general situation where you have a boost isometry. So in Minkowski space, of course, we have that. But another common example that you might encounter something like this is the de Sitter space. Okay. So let me just draw a cartoon of the de Sitter space. It is a space that expands towards the future and also expands towards the past. Okay. And the metric of the de Sitter space is very simple. It's just given by minus dt square plus cos t square, the some sphere. This is like a sphere, d-dimensional sphere, okay? So as you probably have heard of, in de Sitter, there are also different vacua. And one of the particular vacua is the so-called Hartle Hawking state. Which is defined as the vacuum that is with respect to the global time, the time t. So that is the analog of the Minkowski vacuum in de Sitter space. And one way to prepare that Hartle Hawking state is to cut the de Sitter space along the t equals to 0 slice and also continue into the Euclidean signature. So that is, again, very much similar to how we prepare the Minkowski vacuum. We do a weak rotation into the Euclidean signature. What's different is that if you do it for the de Sitter space, the Euclidean part will be a sphere that is attached to the t equals to a semisphere, a half sphere that is attached to the t equals to 0 slice. So something like this, okay? And in the Sitter space, there is also a boost isometry, which is simply that if we look at the sphere, we can think of the path integral as coming from this south pole and evolving upwards, or we can cut the sphere into two parts, the left part and the right part, and think of the evolution as along this kind of slice. Hopefully my drawing makes sense. So there is also a Keeling vector that generates the rotation along one of the angle of the sphere, okay? So that is very similar to the flat space discussion we just had. And that tells you that if we cut the t equals to 0 slice into two halves, the left half and the right half, and we can also continue along this, the Lorentzian continuation of this Keeling vector, that will give us some a Rindler horizon that looks like this. Okay. Maybe it's better to draw a Penrose diagram of the Lorentzian de Sitter space, and the Penrose diagram just looks like a square, and the t this will be the t equals to 0 slice. And there is an analog of the Rindler wedge, which is the right part of this diagram. That is the so-called static patch. And there is a famous statement that if you choose the global vacuum or the Hartle Hawking vacuum for the de Sitter space, from a static patch observer point of view, that is observer that just lives inside this static patch, the de Sitter vacuum looks like a thermostat with some temperature that you can also work out using the same trick. So here I just want to emphasize that this kind of construction is quite general. It applies to general situation where you have a boost isometry. Okay.
Could you just say the 2-point function would still be the same for interacting theory that you started with?
Yes, yes. The reason that it decays like this, you can basically you can extract this behavior by first looking at the Euclidean 2-point function. So the Euclidean 2-point function is periodic. It's periodic when you have theta goes to theta plus 2 pi. Okay. So for example, in a CFT, which can be a free theory or interacting theory, the 2-point function will look like something like sine pi theta over beta with the scaling dimension 2 delta. And now if you continue these two Lorentzian signature, again, you will get an exponentially decay with respect to the Lorentzian time.
Yeah, but in the Minkowski vacuum, if you go above in your slide, just scroll on top, right there. Yeah, phi tau1 x1 and tau2 x2 in the Minkowski vacuum would still be the same for the interacting theory?
No, the exact form will not be the same. The exact form of the 2-point function will not be exact. This is the
then how would we conclude that your derivation will go through for interacting theory? Because there you use the 2-point function of the free theory, right?
I'm not saying that this part of the derivation will be exactly the same. I was talking about the derivation up here using the Euclidean path integral. That will be exactly the same.
Okay, all right, thank you.
For a free theory or interacting theory. Of course, depending on the theory that you get, how you really translate the temperature as derived here into more physical observables, that will be different because the theory is different. Okay, so let me move on to the, is that a question?
Yeah. In the last part mentioning about the vacuum, so you're considering the zeta vacuum as a Hartle Hawking state?
Yeah, that's the name. That's the name of the zeta. Well, that's one of the name of the zeta vacuum.
Why did you choose this Hartle Hawking state as a vacuum?
Oh, it's just I want to draw an analogy to the Minkowski case. So as you see, the Hartle Hawking vacuum is defined as a vacuum that with respect to the global time coordinate t. So it's kind of an analogy to the Minkowski vacuum. Of course, this statement is not entirely true because in the Minkowski case, there is no particle, but there is particles in the Hartle Hawking vacuum. So here I just want to draw an analogy and argue that there is a similar construction and there is a similar boost symmetry in this case that can tell you that the Hartle Hawking vacuum looks thermal if you are observer in the static patch. So it's just another example where this derivation works. Okay.
Yeah, hi, I have a question. So why do you have a half sphere on the t equal to 0 slice rather than a full sphere?
Oh, yeah, maybe I should explain this a little bit better. This is not really the focus, but let's see. So the reason is that, let me just write down the metric again and explain. So let me draw a complex plan for the t variable. So here, from the t equals to 0 slice and going upwards, I'm going from t equals to 0 to infinity, okay? And what I meant here is that at t equals to 0, I do a weak rotation. Instead of going along the real axis, I go along the imaginary axis, okay? So I can write t equals to, for example, I theta, and then ds square will be d theta square plus cosine square theta d omega d square. And if you look at this careful enough, this will be the metric of the d plus 1 dimensional sphere, and it ends at theta equals to pi over 2. Okay, so the entire sphere will be from theta equals to pi over 2 to theta equals to minus pi over 2. That will be the entire sphere. So if you go along this red line, that will be the entire sphere. But to go to the Lorentzian signature, I'm cutting it along the equator and continuing to the Lorentzian signature. So it will just be a half sphere. Does that answer your question?
Yeah, thanks.
Okay, thank you. Okay, let me move on to the Lorentzian perspective of deriving the fact that the Rindler space has a finite temperature. Okay, so the idea is that in Lorentzian signature, we don't talk about Euclidean path integral anymore, but we talk about stuff like mode expansion and exciting a particle and stuff like that. And so to do this is much more restrictive in some sense, because I need to write down a well-defined mode expansion. Usually we only know how to do that for free fields and do it perturbatively. So it's much more restrictive than the Euclidean method, but it still brings some new perspective. So let's just consider a free scalar field in arbitrary dimensions. The dimension really doesn't matter too much in this discussion for the reasons that I will be mentioning. So as you all know, that if we can, in the Minkowski coordinate, it's super easy to write down the mode expansion for the scalar field. It will just be some integral over momentum, will be some vector, divided by some normalizing. Well, let me just focus on the two-dimensional case, but because that's what I've written in the note, but it's not really, nothing really depends on it. It will be in 2 dimensions. So it will be the omega, the frequency of the field, and you have the annihilation operator of the scalar field phi, that is with wave vector k times e to the minus I omega t plus IKT IKX plus AK dagger e to the I omega t plus minus IKX. Okay, so let me emphasize that the annihilation operator multiplies the positive frequency solution. Okay, that is the convention people usually choose. And what I mean by positive frequency solution is that this solution has the property that if we send t to be I infinity, this solution vanishes, goes to 0. So omega, the frequency here is some number that is greater than 0. So that is the definition of the positive frequency solution. Or in other words, in a more mathematical way to say is that this solution.
Sorry, do you mean t equal to minus I infinity?
Let me see. Yeah, sorry. T, yeah, that's embarrassing. T equals to minus I infinity, this solution goes to 0. Or another way of saying that is that the positive frequency solution is regular in the lower half plane for T, okay? But it blows up if you take T equals to I infinity as what I just did. So that is the mode expansion in the Minkowski coordinate. But on the other hand, now we want to consider the Rindler coordinate and do a mode expansion in the Rindler coordinate, because that's the mode expansion that will be suitable for a Rindler observer to describe the particle excitations in the Rindler space-time. So again, we have a left Rindler wedge and a right Rindler wedge. So if we consider a field phi that is in the entire space, let's, for example, choose a time slice here. Well, we don't really need to choose a time slice, but the entire space will include both left and right. That's what I want to say. And the mode expansion will now include 2 sets of mode. One set of mode is in the left wedge and the other set is in the right wedge, okay? So let me just write down schematically what the mode expansion will look like. You will have two sets of creation and annihilation operator. Let me call them B as opposed to A. So you will have B omega left times some function V omega plus B omega left dagger times V omega, the complex conjugate of this function, plus, let me first write it down and then explain. U omega complex conjugate, okay? So because we have both the left wedge and the right wedge, we have two sets of modes. So let me explain. So the B left and B left dagger are the annihilation and creation operator to annihilate and excite the particle that is in the left ringlet wedge. And similarly for these two operators. And what are V and U? So the important thing is that just as what we did for the Minkowski case, the V should be also a positive frequency solution. But now it will not be a positive frequency solution with respect to the Minkowski's time t anymore. It will be with respect to the Rindler time eta, okay? And let's first look at the right wedge. So in the right wedge, if we increase eta, we go upwards, okay? So we know that the U omega should have a form. Here I only write down its dependence on eta. It should have a form that is like e to the minus I omega times eta, okay? That will be a positive frequency solution in the right wedge. What about the left wedge? An important subtlety is that if we go back to the beginning how we define the eta coordinate, we defined basically, let me see, where is it? Well, anyway, let me find it. We defined it here, yeah. So T is equal to R0 times sinh eta. If we are in the left wedge, in which R0 is now negative, as we increase eta, T actually decreases. So that tells us that in the left wedge, as we increase eta, we actually go downwards, okay? So that tells us that, that in the left wedge, the positive frequency solution should be rather e to the I omega eta. So in all of these equations, omega is a positive number, okay? So that is just a difference between the definition of the positive frequency solution in the left wedge and the right wedge. Okay, so now, now we have written two different forms of the mode expansion for the scalar field, okay? And it's the same scalar field. So if we already know what V and U are, what these functions are, we can simply do a so-called Bogoliubov transformation, which tell us how the creation and annihilation operators are related to the Minkowski creation and annihilation operators. So that is a straightforward but kind of a tedious exercise that you can find in many textbooks. But actually here I just want to mention that there is a trick that is due to Anru in his original paper that you don't really even need to know what the explicit form of these functions are. You just need to know how they depend on the eta coordinate. And then you can essentially work out all the physical consequences. So let me say a little bit about that trick, because I find it quite useful if you didn't see that before. The idea is that here, let me explain the idea. Let's say that we have a U omega. So this U omega is a function that is defined only in the right wedge. because it is a mode function in the right Ringler wedge. But the idea Anru had is that we can start from this function in the right wedge, and by doing some analytic continuation, we get a function that is supported both on the right wedge and on the left wedge. And if we get that function, then that function will be defined on an entire spatial slice. And you can show that the function will also be uniquely determined in the future wedge and the past wedge as well. So the idea is to start with a function u omega in the right wedge and find the appropriate analytic continuation such that the observation is that there is an analytic continuation such that the function that you get is a purely positive frequency Minkowski mode. Okay, so that is the important observation Anru had. So let me just say that again. We start with some mode function here, and we do some analytic continuation and define the continuation here. And what he argued is that there is a particular analytic continuation such that the combination of this analytic continuation and the original function on the entire space-time only involves positive frequency Minkowski modes, but not negative ones. Okay, so what is this analytic continuation? So although I said that this section will be about the Lorentzian perspective, in fact, I still need to use some notions in the Euclidean space because that is really convenient. In the Euclidean space, I've told you that we can think of the Minkowski vacuum as coming from a Euclidean path integral in the theta direction. And if we remember that theta is equal to I eta, the way that we can go from the right wedge to the left wedge is simply translating eta in the imaginary direction by amount pi. So we can start with the function in the right wedge, and by analytic continuating eta to eta plus I pi or eta minus I pi, we go to the left wedge. The question now is which one should we use when we do the analytic continuation? Okay. If we go back to the Euclidean picture, that will essentially be boils down to either go in the lower half plane or by going in the upper half plane. Okay, so that's the idea. Which one should we use? And the important observation that Anru pointed out is that there is analytic continuation such that it gives a purely positive frequency Minkowski mode. And what is the defining property of a purely positive frequency Minkowski mode is that it is regular in the lower half plane for the Minkowski time t, but it blows up in the upper half plane. So if we want this analytic continuation to satisfy this condition, we better continue it in the lower half plane rather than upper half plane. Okay, so that's the kind of a convoluted logic behind this trick. But after we get this logic done, is the final result will be really simple. Let me just tell you that going through the lower half plane will correspond to sending eta to eta minus I pi rather than eta plus I pi. And if we started with well, let me see. I think I have some notation problem in my note. Anyway. Yeah, okay, yeah. So let me start with the U, okay? U looks like U is e to the minus I omega eta. And as we take eta to eta minus I pi, it becomes e to the minus I omega eta, and you get e to the minus pi omega, okay? And as I said, we will interpret these as now a mode function in the left wedge, And what will be this mode function in the left wedge? It will not be the positive frequency solution in the left wedge, because that depends on eta as e to the I omega eta. But it will be the complex conjugate of that. In other words, it will be the negative frequency solution in the left wedge. So that tells you that this will be e to the minus pi omega times v omega, the complex conjugate of that. So after all this argument, what I argued is that the combination u omega plus e to the minus pi omega v omega star will be a function that is supported on the entire space, and you can continue into the future and past wedges as well. It will be a function defined on the entire space, and it will only have the positive Minkowski frequencies. Okay, so let me call this function f, okay, f omega. And let me also normalize it. So let's say that both the u and v functions are normalized to delta functions using the Klein-Gordon norm. Then there will actually be a coefficient multiplying this combination that, let me just write that down, will be e to the pi omega divided by 2 sinh pi omega, okay? So this is one of the mode functions that we have argued. It involves only positive Minkowski frequency. But this is not a unique one, because here I was starting with a mode function that is in the right wedge to begin with and continue it. But we could have started with the mode function in the left wedge and continue that. And that gives us actually a different mode function. There's a g omega, which is e to the pi omega 2 sinh pi omega. Now is equal to v omega, the positive frequency mode in the left wedge, plus e to the minus pi omega times the negative frequency mode in the right wedge, okay? So these two will be the modes that only involve positive Minkowski frequencies, and their complex conjugates will be modes that only involve negative Minkowski frequencies. Therefore, the idea now is that we can write down a third mode expansion for the field, which is neither the original Minkowski one nor the Rindler one that we earlier wrote down, but it's a one that involves these new mode functions. And it has the, well, let's just write it down. It has the form, let's say C times C omega times F omega plus C omega dagger F omega star plus D omega G omega plus D omega dagger times G omega star, okay? So this is the new mode expansion that we can write down. The nice thing about this mode expansion is that we know that some nice properties of these annihilation and creation operators. Because this mode function is a mode function that only involves positive Minkowski frequencies. We know that if we act this C omega operator on the Minkowski vacuum, we get 0, okay? So just like how the original annihilation operator annihilates the Minkowski vacuum, this C omega acts on the vacuum is also 0. Similar statement, the same statement works for the operator D omega, okay? So that is also 0. So we know some nice property of them. And another nice thing about this mode expansion is that here we know how the mode functions V and U are related to the new mode function F and G. So we know the explicit relation as I have just told you here. So it's super easy now to work out the relation. Yes?
So C is like A, I guess, but what this D is the coefficient of G omega, and G omega is supposed to have negative. It's for the negative thing, right? Negative.
No, both C and D will both F and G are positive Minkowski frequency modes. They will, yeah. Does that answer your question? They will not be a single frequency mode. There will be some linear combination of those.
Okay, yeah, right.
But both of them are positive. They only involve positive frequencies. So
yeah, the stars.
Yes.
The stars are for the negative, right? I missed it.
Yeah, the stars are negative. So they are associated with creation operators. Okay. What I was saying is that the reason that this mode expansion is super useful because now these mode functions are their relation to the Ringler mode functions are explicitly known, as I've told you here. Okay, so we know the relation, and with the known relations, it's now super easy to work out how the operators B left dagger, B right dagger are transformed into C and D, and C dagger, D dagger. Okay, so now it's super easy to work out that, and by these conditions, you can just with a few lines, you can work out that what is the vacuum state as seen by as expressed in terms of the Ringler modes. So let me just write it down. So it will be a product of different frequencies. Of course, in principle, it's also different wave vectors, etc. But I didn't write those explicitly. Some normalizing factor, Z omega, times n omega equals to 0 to infinity. So it has the form of the thermal field double state, which I think you must have learned in Tom's class. Pi omega times n omega, n left and n right. So n left means there are, well, let me just call it n. And n is the number of the Ringler particles that is being excited. So the vacuum state has the form of a product of thermal field double state of different modes. Let me just emphasize one point is that in this entire argument that Anru pointed out, we never really even write down an explicit expression for the mode functions, but we are able to derive this important physical consequence, which I found rather remarkable. What we used is just some analyticity arguments, okay? Of course, in some of the textbooks, you can find derivation, which involves first finding the explicit mode function and do some transformation, etc. And in the end, it gives the same answer, which can serve as a check of this method. So the final physical consequence is that the vacuum state looks like a thermal field double state if you express it in the Ringler modes. And if we, for example, trace out the left system, the reduced density matrix in the right system will be a thermal density matrix. That's another way of saying that the Minkowski vacuum as seen by a Ringler observer is thermal. Okay.
Can I ask a question?
Yes, please.
So how is these model expansion related to the usual model expansion in terms of T and X coordinate? So they are related via Bogoliubov transformation. Is that correct?
you are asking about how is this one related to the usual Minkowski one?
Yeah.
Yes, so I think I didn't work out the detail, but I believe that this F and G, there are some linear combination of the usual plane waves in the Minkowski expansion. Okay.
How can you know it is made of a linear combination?
How do I know it's made of linear combination? Well, let me see. Well, because this F, let's say it's a, as I argue, this F function is a purely positive Minkowski frequencies. And I believe you can expand any positive frequency functions in terms of the plane wave here.
Ah, I see.
Yeah, just as a Fourier transform of that in the spatial direction. Yeah.
I see. Thanks.
Okay. So let me move on to the next part, which I think this part is actually not usually discussed in textbooks, because, but I find it quite interesting. So the idea is that we could also verify that the Minkowski vacuum looks thermal by computing T mu nu. That's what we that's what we usually do when we say something looks thermal, that it has a finite stress tensor. Okay, but if we really want to do this, we immediately first face a paradox. That is, T mu nu in a Minkowski vacuum, the expectation value is exactly 0, right? And it will be 0 no matter which coordinate system you use, because under a coordinate transformation, 0 is still 0, okay? So how come that the T mu nu in the Ringler space will be non-zero, such that it corresponds to a thermal state, okay? So that's kind of a paradox. Of course, this the resolution to this paradox is very simple. It's because that, well, when we talk about the absolute value of the energy, we always choose a 0 point for the energy, right? So we should really view this equation that the T mu nu in the Minkowski vacuum as a definition. Basically, it should be viewed as the stress tensor minus the let me say it this way. The stress tensor in quantum field theory is in general is a UV divergent quantity. So we always subtract the UV divergent part. And if we are a Minkowski observer, we always subtract the UV divergence that is in the Minkowski vacuum. So that's why the stress tensor of the Minkowski vacuum is 0. But if we are already physically an observer that is accelerating the Ringler wedge, it will not be really physical to subtract the UV divergence corresponding to Minkowski vacuum anymore. If we really think that we are a Ringler observer, that we really only lives in the right wedge, it will be only physically sensible to subtract the UV divergence that corresponds to the Ringler vacuum, okay? So because we are subtracting a different UV divergence, we can get a finite stress tensor. Hopefully I made the physical idea clear. But if it's not clear, it will be clear in the derivation that I'm going to do. So let me demonstrate it with a very, very, very simple example, just a massless boson in 2D, massless scalar field in 2D. So we want to understand what is the UV divergence that a Ringler observer will subtract, okay? So to see that, it is very convenient to write the Ringler metric in a slightly different form. So the original way I wrote it is like this, the R square. Let me write it like in a different form, introduce a new coordinate chi. Well, chi now, chi is defined as e to the chi equals to r. So if r goes from 0 to infinity, chi goes from minus infinity to plus infinity. So this is the so-called conformal frame. The metric up to an overall factor e to the 2 chi is just the metric of the flat space again, but it's now a flat space that only covers the right wedge. Okay, the reason that a conformal frame is useful is because here I'm considering a massless scalar. So a massless scalar is a conformal field, and it doesn't really care too much about the factor in front. And if we are now considering the Ringler vacuum, that because we want to know what is the UV divergence in the Ringler vacuum. So let's consider the Ringler vacuum. That will be equivalent to the Minkowski vacuum for the massless scalar in coordinate eta and chi. Okay, so for the massless scalar field, since it doesn't see the overall factor, it will just look at this metric and say, okay, I choose a vacuum that is with respect to the eta coordinate. So that is like the Ringler, the Minkowski vacuum with respect to that. So this construction makes it very easy to work out what is the, for example, 2-point function of the massless scalar in the Ringler space. Okay. And it will be even easier to use a so-called null coordinate or Lie-Kohn coordinate, where u is equal to eta minus chi and v is equal to eta plus chi, in terms of which the metric can be written as e to the minus u minus v minus du dv. Okay, so it's just some more manipulation that you can do. And the reason is because the massless scalar can be decomposed into left going mode and right going mode. And let's just focus in the null coordinate, they are just separated, and it's very convenient if we only want to focus on one of the modes. And let's say we focus on the right going mode. The right going mode will be given by partial u of the field operator, let's say at location u1, v1, and partial u of the field operator at u2, v2, okay? And in the Ringler vacuum, and the 2-point function in the Ringler vacuum, as I said, it's will be given by some Minkowski expression, and it's super simple. Here I'm trying to make all the prefactors right. So the prefactor will be minus 1/4 pi, but the function multiplied by this simple is just the u1 minus u2 square, okay? So that is the 2-point function of the right going modes. Why do we want the 2-point function? The reason is that we want to use the so-called point splitting technique. It's just some name of computing the UV divergence in the stress tensor. And the stress tensor has a very simple form in terms of the, in the case for this massless scalar, TUU, the TUU component of the stress tensor is just given by partial U phi and partial U phi, okay? So immediately you see that if you naively compute the expectation value, you get a divergence because the two field operators are, they coincide with each other. Of course, to better define the stress tensor, as I said, we need to subtract the UV divergence. And the so-called point splitting method of studying the UV divergence is just to subtract the UV divergence we get when we take the U1 goes to U2 limit. In other words, the UV divergence, let me write it like this, UV, well, it's not a very good notation. UV divergence will be equal to minus 1/4 pi epsilon square. Well, epsilon is the distance between U1 and U2, okay. So that is the UV divergence we should subtract if we are renderer observer. Now, we want to, what is the question we want to answer? We want to answer that why is it that the Minkowski vacuum looks thermal in the renderer space? So the actual 2-point function we want to consider will be the 2-point function in a Minkowski vacuum. And then we subtract the UV divergence that correspond to the UV divergence renderer observer will subtract. So what is the 2-point function in the Minkowski vacuum? We want to work that out. The 2-point function in Minkowski vacuum. That's again very simple. It's useful to introduce also the null coordinates du dv. Hopefully you don't hopefully it will not cause the confusion because there's also uv here. But the Minkowski null coordinates uv, they are related to the null coordinates here by the following formulas. Okay, u is equal to minus e to the minus u, and v is equal to e to the v. Okay, so I want to express the Minkowski spacetime into the null coordinate as well, because the 2-point function is again very simple in terms of these coordinates. So partial u of phi at location u1, v1, and its correlation with partial u of phi at u2, v2 in the Minkowski vacuum will be given by the same formula, 1 over 4 pi u1 minus u2 square, okay? And let's now just do a coordinate transformation and express it in terms of the renderer coordinate, the coordinate u, little u and little v, and it becomes partial u phi still is in Minkowski vacuum, but expressed in the renderer coordinate, it will be e to the minus u1 minus u2 divided by 4 pi e to the minus u1 minus e to the minus u2 square. Okay. Okay, after doing all this work, we are ready to extract the final physical answer. So as I said, this is the 2-point function in the Minkowski vacuum. When we naively take the two operators together, we get a divergent answer for TUU. But as I argued, for a renderer observer, is correct to subtract the UV divergence as given by this formula. So in the end, the renormalized TUU will be given by the limit of U1 goes to U2, this expression here, minus this expression there, which is minus 4 pi 1 over U1 minus U2 square. Okay. I think there's a question in the chat, so let me see. If we substitute this TMU into Einstein equation and solve, will we get the correct renderer Minkowski metric? I think you are considering a back reaction problem, but here I'm just considering quantum field theory on a fixed background. And essentially I'm taking the limit of G Newton to 0. Of course, this entire discussion is still in the Minkowski vacuum, so there will be no back reaction. And the Einstein equation will just be trivial. So the metric will just be renderer and Minkowski. Okay, maybe that is, I'm not sure that I'm answering the question. Maybe you're asking that here I'm getting a non-zero answer. Let me first write down the answer. So after you do this, the divergent part cancel out, and you get a finite quantity that is 1 over 48 pi. Okay, so it's kind of an interesting number. So you get a finite quantity. Of course, this is not saying that there is really a non-zero stress tensor that will back react the space-time. This is just saying that if we are physically a renderer observer and we measure it with respect to our own vacuum, then there's the Minkowski vacuum relative to the renderer vacuum has this finite energy. And we can check that this is the right answer with the consistent with the temperature.
Excuse me.
Yes.
So does this finite contribution from TUU is same for other regularization other than point splitting?
Well, I'm not sure which other regularization you are imagining. Here you can, for example, another way to derive this is to use the so-called conformal anomaly. If you have a conformal field, and you can derive, although the stress tensor doesn't change under a coordinate transformation, it does change under a conformal transformation, and you can derive it using a conformal anomaly. So you get the same answer. But I will think that physically it's the same as the so-called point splitting method. But maybe you are thinking about some other ways of regulating it. I'm not sure.
Oh, okay, thanks. Yeah, I understand.
Okay, thanks. So this value of the stress tensor is consistent with the temperature as measured by the eta coordinate to be 1/2 pi. Okay. As I said, this whole calculation can be also done, I guess, more efficiently depending on what your taste is by using the so-called conformal anomaly. But here we are just using a more explicit calculation to illustrate the physical meaning better. And in the later, I will actually come back to this calculation again and derive another physical consequence of it. Okay. So the last part of the Unruh effect that I want to talk about is the so-called, well, people usually call it the Unruh detector, but it's kind of interesting discussion of, yes, I think there is a question in the chat. Can you show explicitly how TUU is linked to T? I'm not sure what you mean by T. Maybe you can.
Yes, the temperature probably. I'm assuming.
Oh, temperature. Okay. Yeah. Okay. Let me just say what I want to say. So here it is a conformal field. Okay. So let me just write it down. So as I argued that this conformal field lives in the Minkowski space, but as I also mentioned earlier, that you should really think of this eta as having a periodicity in the imaginary direction 2 pi. Okay, so we can kind of think of another way of thinking about the physics is that if we ignore this overall factor, the manifold that the conformal field lives in is an infinite cylinder. Okay, so it's an infinite cylinder with eta. Well, let me continue into the Euclidean signature. So at a Euclidean, the Euclidean direction will have length 2 pi. And this is an infinite long cylinder. Okay, infinite long cylinder. And you can compute the stress tensor just from these because, well, this is a conformal field and it lives on the cylinder, so that we know that if we have a conformal field on a cylinder, there is a so-called Casimir energy, right? So there is a Casimir energy which tells you that the stress tensor in the chi-chi direction should be equal to, in the chi-chi direction times 2 pi should be equal to the Casimir energy, and that should be minus C/12. If I remember the formula for the Casimir energy correctly, And here is a free scalar, so C is just 1, so that is minus 1 over 12. So that tells you T chi is minus 1 over 24 pi, and T eta is eta Euclidean will be 1 over 24 pi, because the trace of the stress tensor should be 0. So just from these and analytic continue to Lorentz signature, you get T eta should be 1 over 24 pi minus 1 over 24 pi. And I guess maybe I'm getting a sign wrong or somewhere. Let me see. Well, I think, oh no, yeah.
Could you?
Yeah.
Can I? Is there some, not in the CFT way of looking at it, but earlier, could you also renormalize by some normal ordering prescription?
Yeah, I think so. Yeah, I think you can. Well, you can do that as well. But here, I think I'm getting a sign wrong somewhere, but I don't immediately see it. I think
the sign is CO minus or plus CO12. That probably depends upon Lorentzian or Euclidean signature, no?
That's a good point. Yes. If you continue, if you continue chi to Lorentz signature, you get a minus sign. Yes, thank you very much. Yeah. So yeah, all these signs are wrong. So T eta is positive and it's 1 over 24 pi. T chi is also 1 over 24 pi. And just by using this, you can get that is 1 over 48 pi. I think maybe this answers the question that is asked earlier. That how do you see that the temperature is 2 pi? Here I just compute the same answer in a different way. Yeah, thanks. Okay, so let me go through this detector story briefly. It's I don't have a lot of formula on this topic, but it's kind of a fun story. That another question? The stress tensor is measured by which observer? Why doesn't this depend on the proper temperature? Well, this stress tensor is the stress tensor that, well, let me say it this way, it's the stress tensor that if you subtract the UV divergence in the Rindler vacuum. I guess the question you are asking is a more physical one, that if we are uniformly accelerating observer, what is the energy that we actually measure, or what is the well, again, I think the statement is that you always measure energy with respect to your proper time, and so you probably will, for example, here I'm telling you that T eta is equal to this amount, but probably you will be more interested in T tau tau or something like that. So I guess there can be some conversion there, but I don't have an immediate, very, very good physical answer to your question. I think we need to think more carefully as how this is measured by an observer. Thank you. So, so there is a cute story here about the detector. It's just after the original Unruh's paper, there are a lot of confusion about how to really physically interpret the result. Of course, from a Rindler observer point of view, the description is so simple. It's just based on the calculation that he does, it seems to be he's saying that if the Rindler observer carries some detector, this observer will see a thermal environment, which is like a thermal bath, and the detector will absorb one quanta of radiation and send a signal, for example. So that's the way to understand that if you already have a detector, you will see a signal as if you are in a thermal environment. But the puzzle that people raised is that how do you understand this process from a Minkowski observer point of view? So imagine that I'm an observer that it just passes by, but I travel along this line. I'm not accelerating or anything. How do I describe it? It seems to be a puzzle because originally in the Minkowski vacuum, if I'm a Minkowski observer, I see no particle whatsoever. So how come that a particle suddenly appears and gets absorbed by this accelerating observer's detector? Like the particle emerges out of nowhere. So let me highly recommend you to read this paper by Anru and Ward, which I actually revisited when I was preparing for this lecture. And I find it really interesting. It's a paper in '84. It's very clearly written. But let me just summarize a bit the main idea. So let's consider that we have a detector that is a two-level system with level spacing omega, okay? And suppose that, let's say this detector is just a single spin, and initially we prepare it in the down state at some very early time, so it's down state here, and the observer starts accelerating with this detector. And let's suppose that this detector is coupled to the outside world, to the scatter field that we were discussing, by a coupling that is like some epsilon, some function epsilon as a function of eta times sigma x. So there's a coupling times the field phi. Okay, so it's just a standard coupling that you might have of your equipment and the environment, which in this case is the scatter field. So this epsilon eta is some small window function, which we are imagining originally is zero, but in some intermediate time, we turn it on a little bit and turn it off at late time. And then we ask, what is the state of the detector at late time, okay? And here we are not going into the details of the calculation that Anru and Ward did, but just based on this very simple physical setup, we can just write down schematically what the state of the system will be when eta goes to plus infinity, so at very late time. So schematically, the state will look like, it has some probability that nothing happens. So if nothing happens, the state will be remaining vacuum state, tensor product with the down state of this detector. But there is some small probability that is proportional to this eta function that your detector detects a particle. So what will be the state after it detects a particle? That will be some small coefficient, let me call it epsilon tilde, which you can compute if you walk it through, times an annihilation operator with frequency that is equal to omega divided by A in the right wedge times vacuum state and up, okay? So let me remind you this B, what is this B? That is the operator that we define when we write down the Rindler mode expansion, and it's an annihilation operator in the right Rindler wedge. The reason that it is an annihilation operator is just because we know what happens from the Rindler observer point of view, that my detector detects a particle from the environment. So there is a particle that gets annihilated from the environment, and my spin becomes in an up state. And the frequency of the annihilation operator, you can work it out. It is given by omega divided by A, okay? So again, this factor omega is simple to understand. It's just because I need energy omega to change my spin from down to up. But this A is related again to the fact that there is a conversion between the regular time eta and the proper time of this accelerating observer. So again, a factor of A pops up here. Now, to understand what a Minkowski observer will actually observe, we can do a very simple thing, that is we can express this B operator in terms of the creation and annihilation operator that I defined here as the C operator and D operators here, because those operators are they have a clear property with respect to the Minkowski time, because this D will be the creation operator of Minkowski particles, and C, for example, C will be the annihilation operator of Minkowski particles. So the final result that we get if we express B into those will be psi equals to, again, you have this state minus I epsilon theta, some normalizing factor e to the pi omega divided by A, 2 sinh pi omega divided by A, plus now there is a linear combination, which essentially is similar to the linear combination that we worked out earlier, e to the minus pi omega divided by A, C, so this is a plus sign, C dagger omega equals to big omega divided by A, acting on the vacuum upstate. So I'm just using the Bogoliubov transformation that you can work out to relate the operators. And we know that the D operator acting on the vacuum state gets 0. So we can just eliminate this term. So we don't have that term. And you immediately see a very interesting result that what's left is a creation operator acting on the Minkowski vacuum state. Okay, so that tells us that from the Minkowski observer point of view, a Minkowski particle is being emitted rather than being absorbed, because there is a creation operator acting on the vacuum state. So this is the short explanation of the puzzle that I mentioned earlier, that what the Minkowski observer see. There's a much more detailed discussion in this paper, which I recommend you to check out. Okay, so I got about like 25 minutes left. So let me just jump into the black hole discussion. I don't have too much prepared for that anyways. So of course, for the black hole discussion, the most classic reference is the original paper by Hawking, which I definitely also recommend you to read. It's a very classical paper. But here I will be using some analogy with the Unruh's effect to say something about the black hole. So for a black hole, the main difference from this previous discussion is that there is a real horizon due to the space-time curvature, rather than a fictitious horizon that, if I didn't really mention it earlier, but sometimes the light cone is called the Rindler horizon. It's the horizon that that will essentially plays the role of the real horizon for accelerating observer. Okay. But for the black hole, there's a real horizon due to the space-time curvature. However, they certainly bear a lot of similarities just because of the equivalence principle, which says that at least locally, acceleration pretty much equals curvature. So there is a more direct relation between the black hole and the Rindler space that I was mentioning earlier, is that the near horizon geometry of a black hole is given by the Rindler space. So let us just walk this through if you did not check this fact before, but I think probably you have heard this in many places. Let's just consider the structural black hole metric, which takes this form. So you have a two sphere, and the idea is that we want to look at the near horizon geometry. So we expand around the horizon, around r equals to r structured, the structural radius, and only keep to leading order in the difference of r minus rs. There is a question in the chat. If no classic observation is executed, then what quantum state will the to be observed system be? In fact, the Ringler spacetime of well, so this is just the I guess this is just the answer. This is the state of the system. When you really do an observation, the wave function collapses into one of the eigenvalue. Let's say you measure in the sigma z basis, then the wave function either collapse into these or collapse into that. And there is a probability that it will collapse into this and another probability that it collapses into that. So maybe that, I'm not sure whether that is the question you're asking about. Okay, but let me move on to the black hole because we are running out of time. And if we expand it, it looks like e to the minus, sorry, not e to the minus, well, r minus rs dt square plus rs dr square r minus rs. Plus the sphere is essentially a constant radius when we are very close to the horizon. And the trick is to introduce a new coordinate, a rho coordinate, which is related to r by demanding that the rho is equal to rs divided by r minus rs dr. Okay, and you can walk it through and see that rho is equal to 2rs square root r minus rs. And in terms of the rho coordinate, you immediately see that the metric is now given by minus rho square dt square 4r structural square plus the rho square plus rs the omega square, okay? So up to a factor 4rs square here, it will be the Ringler metric that we have already discussed. So, and the way we relate we can further translate t into the Ringler time by eta equals to t divided by 2rs. That tells us that the temperature in terms of the coordinate t, the inverse temperature will be 2 pi times 2rs equals to 4 pi times rs, okay? And you might ask, why is the temperature in terms of T now a physically sensible thing to talk about? Because I've always been emphasizing that we should really talk about the temperature as measured by the proper time. But the crucial thing is that very far away from the black hole, taking r to infinity, this T is the proper time of a faraway observer because this factor just becomes 1. So this temperature or this inverse temperature will be the inverse temperature as measured by a faraway observer, okay? Locally, the proper temperature at some radius r, the proper temperature will be different because we cannot ignore this warp factor anymore. And let me just write down the formula. The proper temperature at radius r will be given by 1/4 pi structural radius times 1 over structure radius divided by r, 1 minus that. And it diverges at the horizon. I believe that Professor Maldacena has mentioned this point in the class. So notice one point in this discussion, I've secretly assumed something. That is, I assumed that the left Ringler wedge also exists. But if we just think physically about the black hole, there is no reason to really expect that, because originally the structural radius, we are expanding outside the horizon, so r is always greater than rs, and rho is always a positive number. But here, to use all the Ringler or the Unruh argument, I have to assume that I'm in a Minkowski vacuum, which is defined on both the left Ringler wedge and the right Ringler wedge. So in fact, this argument only applies for the so-called maximally extended structural solution, which will be the Penrose diagram of which takes the following form. So if you draw the Penrose diagram like this, then this argument walks through, and it tells you that as an observer that lives far away in the Minkowski space, the observer sees a finite temperature. Okay, so in particular, this observer will see both outgoing and incoming radiation. Okay, in terms of the earlier discussion I had with if you remember the massless scalar discussion, the point splitting discussion, that means that this observer far away will see both the TUU and TVV be non-zero. Okay, so the observer sees both energy fluxes. So this is the so-called Hartle Hawking vacuum for the black hole, which you can also do a similar trick by going into the Euclidean space and derive various facts about this vacuum, which I believe Professor Hartmann talked about in his class. And the crucial property is that this vacuum describes a black hole in equilibrium. The reason that it can be in equilibrium is because there is an incoming flux that is feeding the black hole, and the black hole is also evaporating radiations outwards at the same time. And the two effects balance out. But there is another vacuum for the black hole that is the so-called Unruh vacuum. And the Unruh vacuum is defined in such a way that there is only outgoing radiation but no incoming radiation. So we should think of this as a vacuum that is more appropriate to describe a real life black hole, because a real life black hole, well, we are not really radiating anything to the black hole, but we are getting, if we are really far away, we are getting Hawking radiation from the black hole. Okay, so interesting. Let me use this toy example of massless scalar field in 2 dimensions to illustrate one important property of the Unruh vacuum that people usually talk about, is that the Unruh vacuum is singular on the past event horizon. In other words, let's imagine that in this diagram, if I only have outgoing radiation and I remove all of the incoming radiation, I don't have anything incoming, then the stress tensor of the quantum field will be singular on the past horizon. And it will also be singular there, be singular on the past horizon. So let me go back to, let me demonstrate this using the Ringler example, the Ringler in flat space example. let me first end this discussion and then go to the questions. Because I'm almost done. So let me go back to the fast-based discussion. So and draw an analogy for the black hole later. So in the fast-based discussion, the analogy will be that if I'm an observer in the Ringler wedge, I'm not considering the Minkowski vacuum. I'm considering the Ringler vacuum for the incoming modes. Ringler for incoming and Minkowski for outgoing, okay? So the reason that I choose if I'm a Ringler observer, the reason I want to consider this vacuum is because I want to consider a situation where there is no incoming radiation in the black hole case. So in the Ringler setup, it will be no particles that travels to the left. There are no particles like this, okay? And we want to derive the fact that in this case, the stress tensor will be singular on this line, okay? And how do we derive that? We can basically repeat the same calculation that I done before, but in a kind of different way. Now, rather than considering the Minkowski vacuum and subtract the UV divergence corresponding to the Ringler vacuum, I want to do it in an opposite way. I want to consider the Ringler vacuum. Let's consider the incoming modes in the Ringler vacuum, and later subtract the UV divergence in the Minkowski space, okay? So this is just, again, this is the formula that we wrote down earlier, but with U substituted by V, because now I want to consider incoming modes rather than outgoing modes. And if we consider the stress tensor in Minkowski coordinate, TVV, if you remember, U is like this direction and V is that direction. And TVV, let me just give you the final answer. It will be given by -1/48 pi V square. If you are interested, you can check this result by yourself. It's exactly the calculation using point splitting that I've done earlier, but doing it in an opposite way. Here we are subtracting the UV divergence in the Minkowski vacuum. And the crucial property is that it diverges on the V equals to 0 slice, okay? What is that? What is the place where V equals to 0? Is this line. So the stress tensor diverges there. And in the black hole setup, in the black hole context, the analogy would be that the stress tensor diverges here. Of course, here I'm drawing an analogy. It's in this flat-based discussion, it's very subtle that which UV divergence we subtract. In general curve space, this notion of subtracting a vacuum divergence is not so well defined because in general, there's no Keating vector that really gives you a notion of vacuum state. But nonetheless, you can generalize the point splitting idea to curve space. And this has been done by some people very carefully for the black hole, for the real black hole geometry. And the final conclusion remains the same. So the qualitative lesson that we learned from Minkowski space still holds, that if we have an en-route vacuum, the stress tensor diverges in the past horizon. In a note that I will upload later, I have a reference for a paper that did this careful calculation. If you are interested, you can check that out. So it might seem a problem that for the black hole, for real life black hole, there is some singular behavior in the stress tensor for the quantum fields that is propagating on the black hole background. But actually, this doesn't really happen. The reason is that the real life black hole is always formed by some gravitational collapse, right? So there is some matter that is falling in of the black hole. So this is some matter shell that is falling into the black hole. And we should only trust the Minkowski, we should only trust the Schwarzschild solution and the quantum field calculation that we were discussing when we are outside the matter shell. So only in this region we can trust the calculation. But inside the matter shell, the metric will just be Minkowski spacetime, and it will not be given by maybe what I say is not exactly correct, but inside the shell, it will not be given by the Schwarzschild metric anymore, and we cannot apply the discussion that we had earlier. What happens is that the would-be singular past horizon will be always hide behind the collapsing matter shell. And in a real-life black hole geometry that is formed from collapse, there's no singular stress tensor whatsoever. And finally, let me end by noting that there is a third vacuum that people sometimes also talk about, is the so-called ball wheel vacuum. That is the vacuum with no radiation whatsoever. So it will be a vacuum where if I'm an observer far away, there will be no radiation, no outgoing nor incoming radiation. And just by generalizing this discussion a little bit, this vacuum, the stress tensor will be singular on both the future and past horizon. So this vacuum doesn't really play an important role in the discussion of black holes, but it will be essentially the vacuum that is describing the quantum fields outside a star. Basically, because outside, let's say this is the star, that the star tends to some finite radius r, and outside the star we see no radiation coming out or coming in. And if there is no star and we continue the quantum fields inwards, we will find some singular stress tensor. But of course, that is removed because there's inside the star, we cannot trust the Schwarzschild solution anymore. Okay, so I guess that's all I wanted to say. And let me perhaps come to this question that is asked earlier in the chat. So in the black hole case, if until the page time, no classic observation is executed, then should we consider the black hole as missing of black hole of all possible masses instead of microstate of mass page? I'm not sure exactly what it means because the energy is like a gauge charge in general relativity, so it's a fixed number and it is always conserved and it doesn't change. Even if you do some, measurement, the total energy of the space-time is a fixed number. But perhaps you are saying that, yeah, I'm not sure entirely what the question is referring to. Is this set of vector an exhaustive list? Well, I guess it depends on how you really define vacuum in the curved spacetime. In general, there's no clear definition of vacuum. Even in this evaporating black hole case, there is no clear. When I say vacuum, it's kind of a vague notion because there is no really a time-like Killing vector to let me really define a vacuum. So I think the word vacuum applied to this case is just is not entirely accurate, and it will not be an exhaustive list. You can like add a bunch of particles on this, and it will give you a different quantum state. Another question, is the UV divergence any relevance with the EMS firewall? Yes, it is. Yes, it is. Yes. Essentially, the reason that you get a, I think probably you heard this in lectures, the reason you get a black hole information paradox is because there is a large entanglement between the outgoing modes inside the horizon and outside the horizon. And that's the reason why if you only collect the radiation that goes to infinity, you get a thermal density matrix. If there is no entanglement, you will get a pure state. But the point is that if there is no entanglement, there will be a firewall, because there will be essentially, as I argued here, there will be a singularity in the stress tensor. Yes, that's a good point. How is the energy in terms of proper temperature consistent with diffeomorphism? I'm not sure entirely what that means, because energy itself is not invariant under diffeomorphism. Maybe I'm not understanding the question. I mean, we always define, yeah. We always define the energy with respect to some coordinate. Let's say we define the energy with respect to t, and we do a diffeomorphism taking t to t prime equals to lambda t, the energy will be divided by lambda. So it's not an invariant notion under diffeomorphism, at least not naively. The state is described by local temperature. The state is what it is. It's just that depending on the observer, you see different physics. You see different you measure different observables in that state, and the physical notion of temperature depends on the observer. But the state is just the Minkowski vacuum state. It's just a single state. That is not observer dependent. Yeah, I guess that's what I wanted to say, but if people have questions, people can stay and ask, but yeah.
Yeah, so are there any further questions? People want to ask?
Thank you.
Okay, I don't see any other questions in the chat or this thing. Okay, so then let us thank Yiming for his excellent tutorials, and we are meeting in the afternoon, I think, or afternoon or evening for the next tutorials. Just 1 minute, I'll just check the time. Forgot it.
What time again we need to start meeting? Loga sir, I'm asking to Loga.
Yeah, just checking. Sorry, just 1
So
minute.
it's in the evening actually, I think 7:30.
Yeah, evening 7:30, yes.
As per schedule.
Yeah. So,
Okay.
so we will meet at 7:30 Indian time, and for Yikun Jiang, who will be taking the tutorial for Tom Hartman's lectures. Okay, thanks everybody, and see you.
Okay, thank you.
Sorry, is there a question?
Okay.
There's some question in the chat. Sorry.
Well, I think we are. Yeah, I think we are being too obsessed with temperature. I mean, we can compute whatever we want. We can compute physical observables, and we associate something called temperature to those physical observables. I mean, I guess we are too obsessed just with the word temperature. I don't have more to say about the question.
Okay. Are there any other questions people want to ask?
Can I ask you a question?
Yes.
Yes.
In the Juan's lecture, he discussed about traversal wormholes, and by making a shock wave. And in that picture, how is it described as a state you describe as a model expansion? So I'm a bit confused because the particle is some kind of classical notion, and in quantum field theory, it should be described as some wave packets, I guess.
Yes, yeah.
And so in his lecture, does he mean he make us some local excitation, and it's an excitation propagating through the spacetime? Is that correct?
So first of all, I didn't really go to his lecture, so
okay.
I probably don't know what exactly he means. But I think in general, what you said is right. You can think of a particle as some localized wave packet formed by taking superposition of different frequency modes.
I see. Thank you. And I have another question. So consider a symptotic observer and consider he can measure only a part of space-time. I mean, part of some restricted Cauchy surface. And in that case, for example, he can perform measurement on some photons of Hawking quanta. So in that case, can you, so how are these photons entangled with? What is the partner of those photons? So my question is regarding, let's see. So for example, in the Rendler case, the Minkowski vacuum is when you expand it in terms of Rendler modes, it is obviously entangled, which is described by time field double state. But
yes.
For the Hawking radiation, the radiation itself is a physical, so you can really collect some Hawking quanta as a collection of photons. So in that case, how these wave function photons are entangled with?
It's still an entangled state of photons outside the horizon and photons inside the horizon. It's just that in this case, you don't need to accelerate to see the photons. You just, for an observer very far away from the black hole, because of this curvature effect, you are effectively accelerating with respect to the horizon. So with respect to the black hole, so you can directly collect all those Hawking quantas. But the quantum state is still just the entangled state.
So what if he collect only? What if he collect the Hawking quanta for a restricted subregion?
Right. Then, yeah, if you only collect subregion,
so does it make some entangled mixed state?
Let me see. So you are dividing the radiation region into some sub-region and its complement.
Yeah. What I'm in my mind is physically you have a finite size of detector, so that you can only perform measurement on some restricted set of photons. So yeah, in such a situation, how is the state described? So
you can definitely describe it as an entangled state of the photons inside your region and outside the region. So that is similar to what we did in the when we divide the Minkowski space-time into the left and right Rindel wedge. But the thing is now the region that is outside the detector includes both some of the radiation region and some of the horizon. And if you simply consider a mode function in that region, it will have support on both outside and inside the horizon. So it's kind of ambiguous to say whether it's a particle in the horizon or not. But of course, you can also take some superposition of those modes, and that will form a localized excitation in the horizon. And you can certainly say that some of the photons that you detect is entangled with those modes in the horizon. And I'm not sure whether this makes sense to you. This makes it clear.
I see. So it differs from usual thermal state when you just trace out the modes inside the horizon.
That's right. Yeah, it will not, of course, not be the same state because you are using when you choose different region, you are using different different bases, right? You are defining your Hilbert space differently.
I see. Thank you so much.
Okay. Any further questions? Okay, then let's thank Yiming again, and let's meet again at 7:30 Indian time.
Okay, thank you. See you.
Thanks, Yiming.